Hi, my name's Tim Faulkes. I'm one of the developer advocates at Aerospike, and I appreciate you coming to this talk. Today I want to talk about vector databases. This is part of the AI ecosystem, and it's one of those common buzzwords that everyone hears commonly, but it's really difficult for people to understand really what it means. So I want to talk about vectors and what vectors are and work out why people really care about vector databases. So first start, I want to talk about a vector. It's this mythical concept that seems to have gained a lot of traction in the AI world. It's a buzzword, but what is a vector? And honestly, it's really simple. A vector is just a list or an array of floating point numbers. That's all. They can have a number of dimensions, but fundamentally, it's just a list of numbers. When we want to start talking about vectors, one of the most common things we talk about is semantic search with vectors. And really what this means is I want to take source information, and the source information can be images, it can be video, it can be text, it can be documents, it can be objects that have meaning to your business. And we turn them into a vector. We use some form of a model to turn them into a vector, one of those arrays of floating point numbers. Now, these algorithms, these embedding models, are typically lossy. They take the information and they reduce it down into a mathematical representation, but it loses information on as it does that. So it's similar, if you will, to doing something like a JPEG compression. It looks the same, but it's slightly lower fidelity. It's got less information, but it represents that original object in its entirety. Now, that seems fairly abstract. So what I want to do now is go through an example of vectors. When would you use vectors? And we'll see how they work in practice. So let's take an example we're all familiar with. We want to buy a house. So let's say we have a floor area. We want about 2,500 square feet of floor area, and we want about 6,500 feet of land area. And that's all. We don't care about anything else. We're not going to look at number of bedrooms or area or anything like that. We're just focusing on those two dimensions. But in our search, we want to make sure that floor space is twice as important as land area. So something that is closer to those numbers, we want, but it's more important to get close to floor space. Let's say we've got 9 different houses that we're looking at in the area that we're after. They have a variety of land areas and floor areas. And you can see these dimensions in this little table, and they've been plotted on the graph that you can see here. There's a red X which shows this is my sweet spot. This is my 2,500 square feet of floor area, 6,500 feet of land area. Which one of these should I pick? Well, what we want to do is we want to turn those dimensions, the floor area and the land area, into numbers that the computer can make a determination on. So what I've done is I've taken the land area and I've divided each one of those land areas by the largest land area. So in our case, we've got 11,780 is the largest land area in those 9 properties. So I've divided by that. I've done the same thing for the floor area. The largest floor area I've got is 3,896. So I've divided each one of the floor areas by that. So that's sort of normalizing the vector. It's now given me a number between 0 and 1 for each one of those floor areas. And you can see in this table, we've got normalized land, and we've also got normalized floor. And again, they're between 0 and 1. Now, I'm just using a very arbitrary algorithm to do this. This is way simpler than what you do in practice, but it gives you an idea of how you might do it. So we've got our normalized vector. We've got 2 dimensions in our vector. Remember, I said that those dimensions on a vector, the fidelity of it, can get really high. A real example might have hundreds or thousands of items in them. We're only using 2, just because it's really easy to conceive what a 2-dimensional vector looks like. Once we've got our normalized land and floor area, what we want to do is apply a weighting. If you remember, we said we want that land area to be twice as important as the floor area. So I'm going to apply that weighting onto the land area and divide each one of those land areas by 2. So I've got my weighted land areas that used to go from a scale of 0 to 1. They now go from a scale of 0 to a half. My floor areas have no weighting, so they stay the same. They go from 0 to 1. You can see those weighted vectors on the right. So I now have a 2-dimensional weighted vector as a combination of that weighted land and the weighted floor. That's great. But what do I do? What use is this to me? I've got some normalized numbers. Okay. The first thing I want to do now is take the input vector. So what we're searching for, a floor area of 2500, a land area of 6500, and apply exactly the same algorithm. So I'm going to divide my land area of 6500 by the maximum land size of 11,780, and do the same thing for my floor area, 2500 divided by 3,896. And then I'm going to apply that weighting on top of the land area. So this gives me a resulting vector. That resulting vector, again, has two dimensions, and it's got two items in it. The first dimension has 0.2579, second one is 0.6417. What we want to do now is find which of those 9 properties has a dimensionality, has a vector that is closest to that one. Now, what do we mean by closest? In a two-dimensional space, it's fairly easy to conceive. We can plot these on a graph like we've done, and we can see which one is closest in just graph terms. As we get higher and higher in dimensionalities, it becomes harder to work this out. There are two main ways we could think of distance. One is what we call a cosine similarity. This is using a normalized dot product. It gives a number in the range of -1 to 1, and the closer two vectors are, the closer they are to giving 1.0. So if I'm looking at two identical vectors, my result will be 1.0. Another common way of doing this is what we call Euclidean distance. It's the absolute distance between those two vectors. In that case, smaller numbers are closer. For this example, I'm going to pick the cosine similarity. And you can see the formula on the right. Now, it's really just the what we call the dot product. It's a mathematical term, the dot product of the two vectors. You can see the formula on the right, and I'm not going to go through it, but it's a very simple formula, and you can see that it would be easy to program. So if we want to compare our input vector with another vector of, say, 0.3735 and 0.5996, we'll get an output. In this case, it will be 0.9886. So it's close. Remember, 1 is identical. So this is very close to 1. But the others might be closer. So that's just an example. Well, how does a computer do this? We've applied that dot product. The code for the dot product is really, really simple. So you can see I've coded an algorithm in Java in this case, which is taking vectors. In my case, I've got two different vectors. They've got hard-coded inputs, but it's doing a dot product. Now, this algorithm actually works for any length vector. It's not restricted down to a two-dimensional vector. So if we had 64 items in our array or 1,000, the same algorithm would apply. It's a very simple and easy algorithm. All right, so let's go and apply that onto each one of our houses. So we've got those 9 houses, which are our representative sample. And what we want to do is find the one closest to our desired 6,500 square feet of land area and 2,500 square feet of floor area. So I've augmented that table we had before, which had the land area and the floor area, the normalized vector and the weighted vector. And I've applied a similarity algorithm across all those vectors to our desired target vector. And you can see the closest one is 0.9994. So it's really, really close. So property 9 would have been the best one in this case. So what we've just done is we've gone through a cosine similarity algorithm. This is very simple. We've used 2 dimensions because it's really easy for us as humans to picture that on a graph. We can see a graph in 2 dimensions. The same concepts apply to higher dimensions. So as I said, some of these complex items can have hundreds to thousands of dimensions. The keys are every vector must have the same number of dimensions. You can't have one vector having 3 dimensions and another having 5 dimensions. You can't compare them. We normalized our vectors in this case in the range 0 to 1. This is not a requirement. This is just the very simple algorithm I used for illustrative purposes. In reality, if you're using a real AI solution, those weights and the algorithms you're using are going to be found out by running some form of a convolutional neural network or a CNN across it, or some other AI model. Now, the one other key point to keep in mind is you form a vector on your source data. That's our 9 properties in this case. When you do that, you're applying an algorithm to that to get your vector. So in our case, we took the floor area and we took the land area, we normalized it, and then we took the half of the land area because we're applying the weight. To make these vectors have any use, the same algorithm must apply to your input. So in our case, we wanted 6,500 square feet land area, 2,500 square feet of floor area. We applied exactly the same algorithm across it, and then we could look at it. One thing to note is those vectors have no meaning in their own right. You can't take a vector and decode it. Remember, I said at the start, it's a lossy algorithm. It will lose information. And so you can't go back and get that information back. What they're useful for is proximity search. That's what we've done. We've just said, I've got my vector. Out of all the other vectors you know about, which is the closest one? Now, this is what a vector database is really useful for. A vector database can store hundreds, thousands, millions, billions of these vectors, and it stores them in a way that it can do a similarity search across them. Now, the vector databases are fairly simple. They have two main components. One is the storage of those vectors, and the other is the ability to perform semantic search or proximity search on those vectors. Some of the key features you'd look for if you're looking for a vector database. You want them to be very efficient in their storage. You want them to be quick retrieval, and you want them to be able to do that similarity search very quickly. There's a lot of different applications for these. Things like doing fraud detection, recommendation engines. Someone goes and looks up a product, for example. You want to go and say, show me any products that are similar to this product. They might also be interested in that. That's a recommendation engine that does exactly this sort of thing. And for retrieval augmented generation applications. I'll come back and talk a little bit more about those later. All right, so what we did before was a brute force algorithm. We took our source vector and we applied it onto 9 different vectors. That's great at small scale, worked really nicely, but it doesn't really scale very well. So what we're going to look at now is something called HNSW. This is a hierarchical, navigatable, small worlds algorithm. The brute force approach worked well because we only had 9 vectors. We compared every vector against our source vector, and then we sorted the results and found the one that was closest. Now that works really well at small scale, but if you've got billions or, heaven forbid, trillions of vectors, it's not practical to do that. What we need to do is do something smarter. We can't afford the computational cost or the long processing times. So HNSW's attempt to solve these problems. Let me continue that example we spoke about earlier, and I'll show you how an HNSW works. So instead of saying 9 points, let's say we had hundreds of data points. You can see on my land area versus floor area graph, it's now a lot more complex. There's a lot more data points for me to look at. If we as humans wanted to work out what is the closest house to our desired target, you might look at this graph and say, well, the ones on the left are too small. They don't have enough land area, or they don't have enough floor area. The ones on the right are too big. They have too much floor area. The ones on the bottom don't have enough land area, and the ones on the top have too much land area. So it's sort of intuitively throw a whole lot of those points away and form an area that would meet your criteria. So that sort of good area you can see on the right, that would be what we'd do intuitively. Once we've done that, we might throw all those other data points away and just focus on that one area which has all those data points. So you can see how I've now exploded that onto that area on the right. If I now apply the same algorithm again, there's some which are too far away and some which are that don't have enough land area, they have too much land area, too much floor area, and so on. I come down to that sort of blue rectangle you can see on the right there. I now have a very small number of points to look at. Instead of looking at the hundreds of points, I've only got 8 points to look at. So now I can do a brute force algorithm across those 8 points, and it will be computationally very efficient. So this is effectively how an HNSW works. It divides the region that you're looking at, your vector space, into layers. Each lower layer has more data points than the layer above it. The higher layers allow you to traverse very quickly into the areas that you're interested in. As you get to a point that you're interested in, you go down into the lower layer and find more data points. Again, do that traversal until you've reached the bottom. So you repeat that process over and over until you reach a data point that has a small number of points, and you can basically brute force it. This works really, really well. However, a single HNSW, if you've got billions or trillions of vector, one HNSW search can still result in thousands of data lookups. So each one of those data lookups and those point traversals has to be very, very efficient. So Aerospike has implemented a vector database. Our implementation of the vector database includes an HNSW. Now, the advantage of this is Aerospike is still the underlying storage engine. So Aerospike is a very fast key value database. It can look up those data points incredibly quickly. So as I said, you might need to do thousands of those lookups. If you can do each one very, very quickly, it takes the computational time of processing that vector search down substantially. Aerospike is also scalable up to petabytes. And each retrieval is typically done in milliseconds or sub-millisecond. The database itself will store the application data augmented with your vectors and the vector search index. Now, our vector search index is a cache layer on top of the Aerospike database. So you can see on my diagram, I've got two different components. One is that vector search, which is a partition index, and the other is the Aerospike database or the storage layer. That index is partitioned and horizontally scalable. So as you add more compute, your results get faster. It will break the vector space up into a set of discrete chunks, with each node being able to process a set of particular space. So you get a very, very scalable solution. It's also self-healing. If you lose a node, Aerospike will just recover. The nice thing about this is also geometric. It breaks your vector space up geometrically, and so there's no real overlap. If I've got three different nodes, they'll all store different data. Now that works really well unless you've got hotspots. So imagine fraud, for example. I'm doing credit card transactions. All my valid credit card transactions probably look fairly similar to one another. A fraudulent one is probably an outlier. It's further distance away. So that area, if I've got one credit card transaction that's come in, I want to work out what its closest vectors are. Are they the good ones or are they the fraudulent ones? So what I would do is I would apply that, and let's say it's a good credit card transaction. Most of the good transactions have a similar look. So there'll be a very crowded space in that center part where the fraudulent transactions aren't, but the good transactions are. So you might imagine that that one node that is servicing that good part of the credit card domain space is very, very crowded and has a lot of transaction requests. So the cache is actually intelligent, and it will re-replicate some of the data to other nodes to distribute that load out across the other nodes. So it's a really intelligent cache that uses advanced algorithms to solve these problems. Now, when we implemented HNSW, we wanted to make sure it was scalable. As I said, we can scale up to petabytes of data. So having a vector database that sits on top of that can store and process millions of vectors is very useful. One of the big problems with an HNSW is there's multiple different layers in the HNSW. So it might be multiple different updates you have to process all at the same time. Once one has finished inserting, the next one will get inserted, and so on. Now this works really well. It keeps the integrity of the index. However, it serializes those writes. That's really good if you've got a very low write insert rate. We're trying to modify, delete, or update or insert vectors at a very, very slow rate. It gives you very good cohesion on the index. But what if I'm trying to do thousands or tens of thousands of inserts at the same time? That one lock is going to cause a problem. It's going to cause a serialization, and it won't scale well. So the other approach that is common is, let's just let everyone go and do it in parallel. We'll let all those requests come in, update the index, they'll do it in parallel, but remember they're all updating the same data structures simultaneously in different ways. So this has a really high rate of corruption of the index. It's really possible to get conflicting changes that update the same sort of data at the same time, and you get race conditions, and the quality of the index degrades, which will lower the results, the quality of the results you're getting back. Neither of these is optimal. So Aerospike, when we went through, we decided to implement our own solution. And what we did was a combination of those two approaches. We sort of, remember I said that each one of those indexes is geometrically sharded. What we're going to do is we're going to buffer some of the writes to that geometrically sharded part of the data and form a local HNSW. So imagine I've got 1 million writes coming in. I'm processing them and I might get batches of 1,000. So I might do 1,000 updates without touching the main HNSW. And what's going to happen is I'm going to take those 1,000 writes and form a local HNSW. It's local. There's no conflict. No one else can see it. I have the entire thing. Once I've accepted those 1,000 writes, for example, what I'm then going to go and do is lock the main HNSW and then merge my 1,000 writes into my local HNSW into the main HNSW. Because they're already structured in a local HNSW, the merge of those 1,000 writes is far quicker than if I tried to do them one at a time. So this really gives the best of both worlds. It merges the results locally into a local HNSW, allowing parallelization, but then it maintains the integrity of the main index by locking it, the main HNSW. So this is something that we actually have a patent pending on, and it's a very effective solution. There is one drawback. Because we're buffering them, the writes that have come in are not reflected immediately into that main HNSW. There's a period of time, it's normally milliseconds or seconds. So if you go and read the data straight after you've written it, you're probably not going to find that information directly in the main HNSW. It's going to take that period of time to update the main HNSW. In most similarity searches, this isn't an issue. Your data set that you're storing is vast, and having one record be there or not there is not really an issue. If it takes a little bit of time to catch up, then that's typically fine. And this gives you that parallelization across the inserts and updates, which people really need. So that's the end of my talk. I thank you for listening. Hopefully this has sparked some of your attention. AI and vector databases are a very hot topic at the moment. If you're interested, there's another talk coming up by Art Anderson, who's going to be talking about practical implementations and looking at multi-model databases and how to implement RAG or retrieval augmented generation applications based on a vector database. And I strongly recommend, if you found this talk interesting, that you might go and listen to his. It should be an excellent talk. Thank you for your time and enjoy the rest of the summit.